Hi, my name is Awaiz Khan. I am a fourth-year medical student at Virginia Tech Carilion School of Medicine. I'm working with Dr. Bradley Icard and Dr. Rubio, both intensivists at Carilion Clinic. The title of my project is Point of Care Viscosity Surrogate Measurement through Utilization of Smartphone Sensors and Custom 3D Printed Design. So our design was conceived in response to a clinical question. The question was, does sputum viscosity change with administration of commonly used mucolytics in intubated patients, such as hypertonic saline or normal saline? Now this is important because in intubated patients, there is a lot of drying of mucus secretions, and clinicians don't really have any evidence to suggest what intervention is better for prevention of mucus plugs in terms of commonly used quote-unquote mucolytics such as hypertonic saline or normal saline. So we wanted to measure the viscosity at the bedside to see what is actually happening to the properties of sputum. And so traditional viscometers we found were expensive and not feasible to use in the ICU, so we came together and decided we should develop our own device. So our design overview had 5 objectives. So we had a requirement for a tabletop design, consistent repeatable results, ease of use, ability to accommodate 5 milliliters of sample, and a low cost. So the analogous design that we tried to emulate was something related to a cone and cup viscometer, but instead of using complex hardware for sensors, we elected to use gyroscopes of the smartphone. So the principle is that a sample is sandwiched between a cone and a plate, and the plate is stationary, and the cone and the provider's phone would be rotating against the resistance of the sample. Now, the thicker the sample, the more, in other words, the more viscous the fluid, the quicker to decay around the resistance of the sample. So the cone and the phone are launched against the resistance of the sample, and increase in viscosity means the whole apparatus will stop moving at a quicker time. So here is our design, and we define time to decay as time from impulse to 0 radial velocity as measured by the gyroscope from the smartphone. And here you can see this red piece and this orange piece are coupled together, and there will be a smartphone on top. And here is a blowaway piece where indicating the sample well, the exterior ring, the top plate with a cone that is interfacing with the sample, and then all this exterior ring and top plate are coupled to a ball bearing which are rotating independently of the sample well, so the only resistance that the whole apparatus is encountering is the viscosity of the sample. So here is a cross-section indicating how we designed the device to accommodate 5 milliliters of sample. This was all done in SolidWorks and 3D printed. So here's the final result, and you can see the ball bearing, the cone, the smartphone on top, and here's a short demonstration how we launched the apparatus, and it was used by a standard rubber band here. And so to test our device for validation and verification, we intended to measure time to decay through the gyroscope reading, and we defined that as angular velocity equals 0. We postulated that this would be a surrogate for viscosity. And so samples that we tested range from 100 centistokes to 60,000 centistokes, which is about the range that we want for mucus. And we looked at 5 trials per sample. So our hypothesis was that no sample in the well will provide the same time to decay value, indicating a reliable launch mechanism, and then increases in the viscosity of the test samples will increase the time to decay value. So here are results indicating our dry run, which means no sample, and as you can see, the samples ran consistently around 3.1 seconds, so our time to decay value was consistent, indicating we had a good launch mechanism. Moving forward to testing with various viscosities, we can see that as increasing viscosities, we had decreasing time to decay values, which demonstrated that our device had some degree of sensitivity in differentiating a thin fluid from a thick fluid. And so here are tabulated results. And then importantly, here is our p-values for a two-tailed t-test looking at different selected viscosities, showing that our device had sensitivity to differentiate between different fluids. So our design and criteria, we had consistency in measurement, and we were looking to bring this into a 40-patient clinical trial.